the previous session, we have discussed what is called the supremum property of the set of all real numbers. And the supremum property states that every bounded above subset of R has a supremum in R itself. And there is a counterpart of that property regarding infimum as well. That means every subset of R which is bounded below has an infimum in R also. Why? Because if the set of all S such that S subset of R is bounded above, it has a supremum in R itself, indicates that the set of all negative S is bounded below, and the infimum is nothing but the negative of the supremum of that set. So, the supremum property ensures the infimum property and vice versa. And with that in mind, we can start with a new property called the Archimedean property in this part. So, the Archimedean property is a well known property. It is a very important property for the set of all real numbers, which states that if x is a real number, then there exists a natural number which is larger than x. So, this is actually a very interesting point to note, that we know that the real numbers are going up to infinity, the natural numbers are also going up to infinity. So, which is the largest real number? It is definitely a natural number. So, that is answered in this Archimedean property. If there exists a real number, surely there exists a larger natural number. So, we can see the proof of this interesting statement. Suppose there exists no such natural number, or if we are given the proof of Archimedean property, we are going to discuss. Suppose we are given an x belonging to R, and if possible, let this real number, if possible, let this real number x be larger than every natural number for every n belonging to n. Then what happens? The set of all natural numbers n now has an upper bound, which is nothing but x. Okay. So, the set of all natural numbers, if we consider, this is a subset of R which is bounded above by this number x, and hence by supremum property, this set n has a supremum. Say U is the supremum of set n. This exists in R. So, U is the supremum of n means what? If you consider any element which is less than U, or any number which is less than U, that cannot be an upper bound. So, if we consider U minus 1 is strictly less than U. So, U minus 1 cannot be an upper bound. Cannot be an upper bound. Why? Because U is the supremum of the set n, which indicates that it is not an upper bound, means there exists some natural number m such that U minus 1 is less than m. That means U minus 1 cannot be an upper bound. So, U minus 1 is less than m indicates that U is less than m plus 1. But since m belongs to the set of all natural numbers, we have studied that m plus 1 is also a natural number. And now we have, therefore, there exists at least one natural number. There exists a natural number greater than U, which is a contradiction, since our assumption is u is the supremum of the set of all natural numbers. So, we have arrived at a contradiction. Why this contradiction? Because our assumption was wrong. What was our assumption? We have assumed that n is less than or equal to x for every natural number. So, that is not possible, and definitely there exists at least one natural number which is larger than x, as is said in the Archimedean property. So, that is the proof of Archimedean property, and using this we can solve or we can find the solutions of many other problems. The first being a corollary to Archimedean property. If S is equal to the set of all 1 upon n, where n belongs to the set of all natural numbers, the infimum of S is nothing but 0. So, we can prove this using this Archimedean property as follows. We consider the set S as given the set of all 1 upon n, where n belongs to the set of all natural numbers, and therefore, this set can be enumerated as 1, 1 by 2, 1 by 3 and so on, and it will go up to 0 because as n increases larger and larger, this is going to 0. So, it is going to 0 finally. So, we can say that 0 is a lower bound of this set S. It is a lower bound of the set S. So, as we have discussed in the beginning, the supremum property ensures an infimum property as well. So, now S is a subset of R which has a lower bound, and hence by the infimum property it has a greatest lower bound as well. So, we can take that lower bound to be L. So, L is equal to infimum of S exists in R. Why? This follows by the infimum property of R. And L is equal to infimum of S means if we take any 1 by n is strictly greater than or equal to L. Why? Because L is the infimum and S is the set of all 1 by n. So, this condition holds. Okay. Now, let us take an epsilon greater than 0. Let epsilon greater than 0. So, this indicates that 1 by epsilon is also greater than 0, and 1 by epsilon is a real number. So, 1 by epsilon greater than 0 it belongs to the set of all real numbers R, and hence by applying Archimedean property, we have there exists at least one natural number n or m you can say, such that 1 by epsilon is less than m, or we can have m is greater than 1 by epsilon. Therefore, we will be having 1 by m is less than epsilon, because if we take the reciprocal, the inequality gets reversed. So, 1 by m becomes less than epsilon. And we have a result just now, 1 by n is greater than or equal to L for every natural number. So, we can have combine these two results and we will be having 1 by m which is greater than L. 1 by m is greater than L. So, we can have combining these two results, we will be having 0 is less than or equal to L, which is less than your 1 by m, and that is less than epsilon, because L is the greatest lower bound. L is definitely less than 1 by m, and so 1 by m is greater than L, which is less than epsilon. And this is holding for some arbitrary epsilon greater than 0. So, since epsilon is arbitrary, now we have the result that 0 is less than or equal to L, which is less than epsilon for every epsilon greater than 0. So, we have studied in an earlier class that if we have such a real number, then this forces L to be equal to 0. Therefore, the infimum of the set of all 1 by n, where n belongs to the set of all natural numbers, is now equal to 0. So, that completes the proof of this result. So, that is the proof of this corollary. Now, the second corollary is that if t is greater than 0, then there exists an nt belonging to n, the set of all natural numbers, such that 0 is less than 1 by nt is less than t. So, t is given to be greater than 0. So, the proof of this corollary is as follows. Given t is greater than 0. Now, look at this corollary and the previous result that we have just now proved. We had the set of all s is equal to 1 by n having infimum as 0. So, 1 by nt, where nt belongs to n, is one of the elements of that set S, and therefore, we can apply that corollary to the proof of this one. So, we know that infimum of the set of all 1 by n, where n belongs to the set of all natural numbers, is equal to 0. Therefore, infimum means it is the greatest lower bound. So, t greater than 0 indicates that t cannot be a lower bound of the set S. Why? Because the infimum is equal to 0 and t is greater than 0 means t cannot be a lower bound of this set. Therefore, what does this indicate? There exists at least one nt, one natural number, such that 1 by nt will be definitely less than t, because there should be at least one element of that set which is less than t. Otherwise, what will happen? T will become a lower bound and we will arrive at a contradiction. And 1 by nt is definitely greater than 0 as well. That completes the proof of this result. 0 is less than 1 by nt is less than t. So, that completes the proof of the second corollary. Now, we have a third corollary which states that if y is greater than 0, then there exists a natural number ny such that ny minus 1 is less than y less than ny. So, that means every real number can be placed between two natural numbers. So, these are the properties which shows how the real numbers can be arranged on the real line. So, if y is a positive real number, then there exists a natural number ny such that ny minus 1 less than y less than ny. Now, let us look at the proof of this result that also follows from Archimedean property, and one more property we will be applying in the proof. So, proof of the third corollary. Suppose we consider the set EY to be the set of all those natural numbers such that y is less than m. So, why we are considering such an EY is because we are given y to be greater than 0. So, definitely y is on the right side of 0. Somewhere here you have your y. So, we can find some natural numbers which are greater than y. That is why there is nothing wrong in defining a set like this. EY is equal to the set of all m or natural numbers for which y is less than m. So, we can say that EY is definitely not equal to 5. Why? Because there exists at least one natural number for which y is less than m. That is ensured by Archimedean property. Therefore, EY now becomes a non-empty subset of the set of all natural numbers. EY is definitely a subset of n. Why? Because we are taking EY to be the set of all those natural numbers which are greater than y. So, EY now is a non-empty subset of N. Therefore, by well ordering property that we have discussed previously in one of the sessions, by well ordering property, there exists a least element, say Ny in EY. There exists a least element Ny in EY. Ny is the least. So, Ny belongs to EY indicates that Ny is a natural number which is greater than Y because of the definition of EY itself. So, we can write Y is less than Ny. Therefore, also if you consider the natural number Ny minus 1, this does not belong to EY. Why? Because Ny is supposed to be the least. Hence, we can have Ny minus 1 to be less than Y, because if it was greater than Y, definitely it would be an element of EY, but it is not so. So, Ny minus 1 is less than Y, and combining with this inequality, we will be getting the inequality like this. So, that is what exactly is given in the third corollary. So, that Ny minus 1 is less than Y less than Ny. Now, using the Archimedean property, we are going to establish that there are some positive real numbers x such that the square is equal to 2, or this is a statement showing the existence of numbers like root 2, square root of 2. So, we have already seen that square root of 2 is an irrational number. It cannot be expressed in the form of p by q, and in this case we are going to establish the existence of such a real number. So, this result shows that there exists some positive real numbers whose square is nothing but 2. So, how it is established is considered as different cases. We are going to use Archimedean property in the proof of this as well. So, let us see the proof. We are going to establish that there exists, it is actually considered as a theorem. So, we can write that there exists an x belonging to the set of all real numbers, positive real numbers actually, such that x square is equal to 2. So, the proof starts as follows. Let us consider a set S is equal to the set of all real numbers such that the square of that number is less than 2. So, S is the set of all those real numbers whose square is less than 2. So, we can say that definitely a real number belongs to this set S. Which is that real number? 1 definitely belongs to S. Why? Because 1 square is equal to 1, and 1, as we all know, is less than 2. Therefore, what is our conclusion? S is a non-empty subset of R. Why? Because 1 definitely is an element of S, and S is a subset of R, we can say, because it is a set of all real numbers for which the square is less than 2. Also, we can say, since 2 square is equal to 4, which is greater than 2, we can say that 2 does not belong to the set S. So, none of the elements or none of the real numbers which are larger than 2 also cannot belong to this set. So, we can say that S is bounded above by 2. Why? Because 2 does not belong to the set S. Definitely the set of all real numbers whose squares are less than 2 should be less than 2. Therefore, S is bounded above by 2, and hence Combining these results, we have S as a non-empty subset of R which is bounded above. Hence, we can apply the supremum property. Therefore, applying the supremum property, there exists a supremum, say X, for the set S in R. Now, what our claim is, we are going to claim that the square of this set X is equal to 2. We are going to claim that X square is having the value 2. So, the existence of root 2 shows that there exists a supremum, or it is ensured by the supremum property, because we have seen that by the supremum property there exists such a supremum, and we are going to show that that supremum when squared gives you 2. So, which is that supremum? That is actually square root of 2. So, by the law of trichotomy, we have two other cases. X square equal to 2 is what we intend to show. So, by law of trichotomy, we have either x square greater than 2 or x square equal to 2 or x square less than 2. So, if we get rid of these two conditions, if we can show that x square greater than 2 or x square less than 2 gives a contradiction, then by the law of trichotomy, it ensures that x square should be exactly equal to 2. So, that is the proof method that we are going to apply here. So, first we consider the case when x square is less than 2. So, case 1, we are going to consider the case when x square is less than 2. So, suppose we can find a number, say 1 by n, such that x plus 1 by n the whole square is also less than 2, we will arrive at a contradiction because we are having x as the supremum of S. So, x is the largest element whose square is equal to 2. So, that is what we are aiming to show. So, if we can prove that there exists at least one real number x plus 1 by n whose square is less than 2, then that contradicts the result that x is the supremum, because there is an element in the set S which is larger than x. So, that is a contradiction. So, that is what we are going to show here. So, x plus 1 by n the whole square is less than 2 means if you take x plus 1 by n the whole square, what we have is x square plus 2 by n x plus 1 upon n square, which is less than or equal to x square plus 2 upon n x plus 1 by n, because n is a natural number, 1 by n square is definitely less than 1 by n. So, this is less than x square plus 2 by or 2x plus 1 upon n, we can write. Because n is common, we can take 2x plus 1 upon n here. So, if we wish to have this to be less than 2, what we require is x square plus 2 by or 2x plus 1 by n to be less than 2, which indicates that 2x plus 1 by n is less than 2 minus x square, or that shows that 1 by n is less than 2 minus x square by 2x plus 1, or n should be greater than 2x plus 1 upon 2 minus x square. Now, you look back to the assumption that we had started with. We had our first case to be x square is less than 2. So, if x square is less than 2, definitely 2 minus x square will be larger than 0. So 2 minus x square is a positive real number. And 2x plus 1 is also a positive real number. So this ratio as a whole becomes a real number. So 2x plus 1 upon 2 minus x square is now a positive real number. Belongs to R plus. So what guarantees the existence of such a natural number? The Archimedean property ensures that there exists definitely such a natural number which is larger than this, and therefore backtracking we will be getting this to be less than 2, which shows that our x plus 1 upon n square will be less than 2, and we arrive at a contradiction. So that completes the first assumption, x square less than 2 is wrong. We cannot take this case. Now the second case we will be discussing in the next session, and we will continue to show that we have a real number whose square is equal to 2. Thank you.